Alright, hello everyone. I hope you guys are doing good. So today I will be discussing the solutions to Codeforces Educational Round 117. This round was held in the afternoon today, and talking about the difficulty, first of all, this was like one of those typical Codeforces rounds in which the first two problems are on the easier side, then problems C and D are moderate, and problem E is kind of hard, right? So it is like kind of balanced round. As you can also see by the number of submissions, they have decreased gradually, so that also points towards the fact that the round was balanced. So yeah, I don't have any complaints with this round. And yeah, let's start with problem A. I will be discussing the first 5 problems from A to E. Okay, so in this problem we have been defined with a term called Manhattan distance, which is a very common term. The Manhattan distance between 2 points is ABS of x1 minus x2 plus ABS of y1 minus y2, where the first point is x1 comma y1 and the second point is x2 comma y2. Now we already have 2 points. One point A is just the origin 0 comma 0 and a point B which is x comma y. Now we need to find a point C such that the Manhattan distance from A to C is equals to half of the Manhattan distance from A to B, and the Manhattan distance from B to C is also equal to half of that from A to B. And we have to find a point C such that its coordinates are non-negative integers. Okay, so let's try to see what's going on in this problem. Alright, so first let's define D is equals to the Manhattan distance between points A and B, right? So D is equals to dA comma B. Now I know that the point B is x comma y and the point A is just the origin, so the Manhattan distance has to be x plus y, because they have provided us with the information that both x and y are up to 50 and are positive. Now I want to find a point C such that the Manhattan distance from origin to C is half of this, which is x plus y by 2, and the distance from C to B is also half of this, right? So let's try to make some equations. The first equation is the distance between A and C should be half of the distance between A and B. Now let's assume that my point C is equals to small a comma small b. So the first equation I can write as the Manhattan distance between A and C is equals to x plus y by 2, and the Manhattan distance between A and C is just going to be A plus B, which has to be x plus y by 2. Now again, if I want both small a and small b to be integers, then x plus y by 2 has to be an integer, which means that for the answer to exist, x plus y must be even, right? So that's the only observation here. So this is the only condition where the answer is going to be -1, where x plus y is odd. So from now on I will assume that x plus y is even. Now this is the first equation, but according to the second equation, I want the Manhattan distance between B and C to also be equals to x plus y by 2, and the Manhattan distance between B and C is absolute value of x minus a plus absolute value of y minus b, and I want this to be equal to x plus y by 2, right? Now there are various solutions to this problem. One of the solution is you either take x is equals to 0 and y is equals to, you either take small a is equals to 0 and small b is equals to x plus y by 2. You can see that this equation is being satisfied there. And you can either take small b is equals to 0 and small a is equals to x plus y by 2. Now what you realize here is that this is a modulus based equation, so you can't just blindly take one of the solutions here. You have to see whether x is greater than y or y is greater than x. So I know that x plus y by 2 will surely be smaller than the maximum value of x or y. So if x is greater than y, I can take a to be x plus y by 2 and b to be 0. That way I am guaranteed that a is smaller than x and b is smaller than y. But if y is greater than x, then I can take a is equals to 0 and b is equals to x plus y by 2, because that way I'm guaranteed that y minus b is positive and x minus a is positive, so that this mod opens in a positive manner, right? So yeah, accordingly if x is greater than y, you can take the second solution, and if y is greater than x, you can take the first solution. So let's just have a look at the code. It's pretty simple. You take in x and y, and if x plus y is odd, then you just output -1 and -1. Otherwise, if x plus y is even and x is greater than y, you simply output x plus y by 2 and 0. But if y is greater than x, you will output 0 and x plus y by 2. And the reason for this is that I'm just assuming that both of these mods open in a positive manner. That is, the first mod opens as x minus a and the second mod opens as y minus b. And if this term has to be equals to x plus y by 2, then that just means that a plus b has to be equals to x plus y by 2, right? And it is pretty evident that this is what the first case says us. So if I take b is equals to 0, then a becomes x plus y by 2, and if I take a is equals to 0, then b becomes x plus y by 2. But the only condition is that this mod has to open positively. So I need to make sure that x is greater than a and y is greater than b. And I know that x plus y by 2 will be smaller than maximum of x comma y, and 0 will obviously be smaller than both x and y. So if x is greater than y, I can take a is equals to x plus y by 2 and b is equals to 0. But if y is greater than x, I can take the opposite. I hope it makes sense. So yeah, this is problem A done. Now let's move to the next one. Alright, let's see what this problem has to say. So first of all, we have been defined what a permutation is. I will assume you guys know what a permutation is. It is basically an array of length n where every element from 1 to n occurs exactly once. So we have three integers, n, a and b, and we know that n is an even number for sure. So what we need to do is we need to print any permutation of length n such that the minimum number among all of its elements in the left half is equal to a, and the maximum element among all the elements on the right half equals to b. Of course, if n is even, we know that the left and right halves are of the same length, that is n by 2. So there is no problem there. And we have to print -1 if there is no such permutation possible. Alright, so let's see how do we approach this problem. So the first thing to notice here is that both halves have a size of exactly n by 2, right? And first, and we already know that one element in the first half has to be a and one element in the second half has to be b, right? So we need n by 2 minus 1 elements in each half, and all of these elements have to be distinct, right? Because one element is a in the first half, and there has to be n by 2 total elements in the first half. So we need n by 2 minus 1 more elements in the first half, and accordingly in the second half. Now, one thing that we can notice here is that a greedy strategy will always work, right? If an answer is possible, we can always construct it using a greedy strategy, and that greedy strategy is this. So after putting a in the first half, so what we want in the problem is that a has to be the minimum element in the first half. So we will try to put, after we have put a in the first half, what we will do is we will try to put the maximum element possible at each stage in the first half, right? And accordingly, in the second half, after we have put b, we will try to put the minimum element possible at each step. And the reason this greedy strategy will work is that we want to have the maximum element in the minimum element in the first half be a, and the maximum element in the second half be b. Now, let's say we are in the first half and we know that we want b to be the maximum element in the second half. So it won't hurt if we take large elements in the first half, because that will only help us in making b the maximum element in the second half. That is why, while in the first half, we will try to put the greater elements in the first half, because that will prevent them from going in the second half, and that will help us to make b the maximum element in the second half. And similarly, when we are in the second half, we know that we want A to be the minimum element in the first half. So it is beneficial for us to put all the small elements in the second half so that it is easy for A to be the minimum element in the first half, right? So yeah, this is the greedy strategy for this problem. We will try to do this at each step, and once we are done, we will just check our permutation if it contains all the elements from 1 to n exactly once or not. And yeah, this greedy strategy will work here. Let's just have a look for better clarity. Okay, so let's see what I'm doing here. So I take a Boolean vector taken which denotes whether I have taken the corresponding ith element or not. Initially everything is false, and V is my final permutation. So the first thing I do is I put A in the first half, specifically in the first position. So I do V of 1 is equals to A, right? And I do taken of A is equals to true. Also, I will put B towards the end. So I have also done taken of B is equals to true. And now what I'll try to do is I'll try to put the greater elements in the first half. So I will eventually start with n, and obviously if I will assign cur is equals to n, and I will try to put cur in my first half. And obviously if cur is equals to a, then I won't put it, so because I already have put it, so I will do cur minus minus. And now I take this while loop, and my initial I is from 2, because I will start from 2 in the first half and go all the way till n by 2. Now, if I reach B at some point, I know that B has to be put in the second half, so I won't consider that, and I will simply do cur minus minus. But if it is not B, then there is no problem. I can insert it into my permutation. So I will do V of I is equals to cur, and if cur is between 0 and between 1 and n, then I will do taken of cur as true, and then I will decrement cur and increment I, and I will go ahead until I is less than equals to n by 2. Now I have successfully constructed my first half. So I mean, I don't know I have successfully constructed it or not. I will check that later, but I have put some elements in my first half. Now I will do V of n is equals to B. That is, I will put B in the second half, and then I will try to put the smaller elements in the second half, starting with 1. And I will do the exact same thing. If I encounter A, I will just go ahead. Otherwise, I will just put it in my permutation. And finally, first thing that I have to check is that all the elements are taken. And the second thing that I have to verify is that the first half, the minimum element in the first half is A, and the maximum element in the second half is indeed B. And if that is the case, then I'm okay. And if that is not the case, I will simply output -1. Otherwise, I will output all the elements in my permutation. So yeah, this is it for problem B. It's a simple greedy strategy that you can follow to solve this problem. Right. So now let's move on to the next problem, which is problem C. Okay, so let's see what this problem has to say. So you have a usual chat of the most famous streaming platform and etc etc. Basically what's happening is that there are various emojis, and specifically there are 2k-1 lines or messages, and in the ith line, if I is less than k, then there are simply I messages, but if I is greater than k, then there are some other kind of messages, right? So what's happening is that in the first line there is 1 message, in the second line there is 2 message, and so on and so forth. In the kth line there are k messages, then in the k plus 1th line there are k-1 messages, and in the k plus 2th line there are k-2 messages, and so on and so forth up till like 2k-1, right? So this is what is going on. So finally what we have to tell is that we have been given a value x, and we just want to tell that what is the index of the first line where our number of emojis, the total number of emojis from 1 to that line, would exceed x. So yeah, this is the problem. It's not very difficult to see how we actually have to solve this problem, but let's see what's going on. Problem C. Okay, so what's given to us is if the line number, let's denote the line number by I. So if the line number is less than equals to k, then number of emojis on that particular line is just I. And if I is greater than k, for example, in the k plus 1th line, you can notice here there are k minus 1 emojis, and in the k plus 2th line there are k minus 2 emojis. So number of emojis is k minus I. Okay. So what we can notice from here is that we can use some mathematical formulae to find out the total number of emojis in lines from 1 to I. And let's see what these formulae are. So first of all, if I is less than equals to k, then what I need to find is, I need to find 1 plus 2 plus 3 up till I, right? This is what I need to find. And this is a very well known formula. This is just going to be I into I plus 1 upon 2. It is just an arithmetic progression which can easily be derived to be I into I plus 1 by 2. But what if I is greater than k, right? So one thing we notice is that let's calculate the case when I is greater than k. So the first thing is that total number of emojis is equal to the sum of all the emojis. So in the first k lines, I will have k into k plus 1 upon 2 emojis, and in the remaining k minus 1 lines, I will have k into k minus 1 upon 2 emojis, because I am summing up all the values from k minus 1 to 1. So the total number of emojis are just going to be k into k plus 1 upon 2 plus k into k minus 1 upon 2, right? Now again, another thing that I can notice is that when I am at line I, when I am at line k plus I, so I already know that when I is less than equals to k, I have something. But let's say I am at I is equals to k plus j, right? So then what happens is that, for example, let's say you are at k plus 1th line. Here you can notice that in the k plus 1th line, there are k minus 1 emojis. So what happens is you need to sum up all the values from k minus 1 to nothing, because this is the first element. But if you start at k plus 2, then you need to sum up all the values from k minus 2 to k minus 1. And to that you have to add k into k plus 1 upon 2. So your total number of emojis are, obviously first you have to add k into k plus 1 upon 2. But after that you have to add something else. And so what you realize is that instead of adding that, what you can do is you can subtract this bottom part from here, from the total number of emojis. So this is what I'm going to do. So let's mark this as tot, or maybe total. So when I'm at k plus j, the total number of emojis that I will have is total. In the prefix from 1 to k plus j, the total number of emojis are going to be total minus this bottom part. And we can clearly notice that the total number of emojis in this bottom part are just going to be k minus j. They are going to be k minus j into k minus j minus 1 upon 2. Yeah. You can clearly notice here that at this position, this very position, you can say that j is equals to 1. So the total number of emojis below it are k minus 1 into k minus 2 upon 2, right? So yeah, you can add them, and then you can easily find out the total number of emojis in any prefix of length I. So now the information that you have is, we have the total number of emojis in every prefix. And once we have that kind of information, what we can do is we can simply apply binary search to solve this problem, because we just need to find out the first index where this prefix sum is greater than equals to x, right? And that can easily be found out using lower bound, or maybe implementing binary search by hand. So let's just have a look at the code for better clarity. Okay, so yeah, this is what I'm doing. This is the I have made this problem over complicated by doing two separate binary searches, but they could have been condensed into one binary search. But anyways, so the total is k into k plus 1 upon 2 plus k into k minus 1 upon 2. First of all, if x is greater than total, then the answer simply will be 2k minus 1. Otherwise, if the answer, if x is less than equals to k into k plus 1 upon 2, then I know that the answer will lie between 1 to k. So I can do a binary search from 1 to k and find out the answer. So this is that binary search. And the third thing is when the value of x exceeds k into k plus 1 upon 2, but it is less than total. So in that case, again, I can do a separate binary search, and I can find out the corresponding prefix sum using these mathematical formulae. And then I can simply output the answer, right? So these are the three cases which were not necessarily should be handled separately, but this is what I have done. So yeah, this is it for problem C. I hope I was able to explain it well enough. So now let's move on to the next problem, which is problem D. Okay, so let's see what we have here. So here we have been given with a pair of integers a comma b and another integer x. Okay, now what we want to do is there are two types of operations that we can do. At each stage, I can either assign a to be the absolute value of a minus b, or I can assign b to be the absolute value of a minus b. So what I do is I choose one of the two numbers from a and b and change them to the absolute value of a minus b. And finally, I have to tell, after doing a set of operations, is it possible that I get an x somewhere? So I can get an x as my first number or my second number, it doesn't matter. I just have to tell whether it is possible or not to get an x, right? So this is the problem D. Let's see how to approach this one. All right. Let's try to see what's going on here. So it will be better if we visualize it using a tree-like structure, because that is exactly what the process is going to look like. So let's try to visualize it. So initially what we have is, we have two numbers, which is a comma b. And without any loss of generality, I can just assume that a is greater than b. So if I assume that, I will have two choices. So AB, absolute value of a minus b, will just be a minus b, and I will have two choices now. First choice would be to convert b to a minus b, and in that case I will get a comma a minus b. And the second choice is to convert b to a minus b, is to convert a to a minus b. In that case I will get a minus b comma b, right? Okay. Now, if we do this naively, obviously there will be exponential types of possibilities that can occur. So to avoid that, we have to make one observation. And that observation is that if a is greater than b, then it doesn't make any sense to go here at a comma a minus b. The only sensible thing to do here is to go to a minus b comma b. And let's try to prove that observation, right? So let's try to see why going to a minus b comma b is just useless for us, and it is always better to go for a comma a minus b. Okay, so now let's try to see where we will lead if we go to a comma a minus b, right? So if we are going to a comma a minus b, what happens is that I obviously know that a will be greater than a minus b. So the first choice that I have is to keep a the same and convert a minus b to their difference. So then I will have something like this. This a will remain a, but this a minus b will be converted to a minus b, which is b, right? And the second choice is that I let a minus b remain, and then a will be converted to b. So I will have b comma a minus b, right? But again, here what I notice is that both of these values I already have with me, right? This a comma b already has occurred here, and this b comma a minus b has already occurred here. So that means that going from here to here is just a waste for me, because that would just lead to recomputations, right? I already have a comma b, I already have b comma a minus b. Obviously, because order doesn't matter here, so a minus b comma b and b comma a minus b are just the same, right? So let's try to write down what we have observed. For a pair a comma b such that a is greater than or equal to b, going to a comma a minus b is useless, right? It is useless because it will never help us. So if we are at a comma b, the only new term that is being introduced is a minus b, and that term is there on the left side as well as the right side, so it doesn't really matter. But if we go to the left side, there will be no extra new terms introduced because the next two values that I will get are those which I already have considered previously. So that will just be a waste of time for me. So what happens is, from a comma b, I will keep going to a minus b comma b, right? So what happens is, I will keep doing this, but obviously there is a limit, right? So I will be at a comma b, then I will be at a minus 2b comma b, then I will be at, so now from here, I will be at a minus b comma b, and now again I have a choice, right? So if I just assume that a minus b is also greater than b, then I will be at a minus 2b comma b, and now if I assume that a minus 2b is also greater than b, then I will be at a minus 3b comma b, right? Because it doesn't make sense to go left. This is a left operation and this is a right operation. In the left operation, I am changing the second variable. In the right operation, I am changing the first variable. And I have already proved that changing the second variable is always useless, because if I try to go further, I will already go to previously explored states. So it is useless. And so on. Coming back here, this will keep happening x times. So let's say the last term here is a minus xb comma b, and let's say that x is the number after which a minus xb becomes smaller than b, right? Right. So my task is to find x. Find x quickly. Because if we do that, I can easily find my answer, right? I can just go simply from a minus b to a minus xb comma b, because in all these middle terms, I can just find out the answer very quickly, because I know that the numbers are just going to be a minus b, a minus 2b, a minus 3b, and so on and so forth. So I think x was given to me in the problem, so let's take it as r, or maybe q. Q is a better choice. So we need to find q quickly, and if we find q, I can just go from a minus b to a minus qb comma b, and I can also check for the availability of x in all these middle terms very quickly. And I can do that because, let's say in the ith operation I get to x, then a minus ib will be equal to x, right? Because the new term which is introduced at the ith operation will be just a minus ib, right? So I know that a minus ib is equals to x. So that means that a minus x is equals to I times b. So I can just say that if a minus x is divisible by b, then obviously I will find an answer in between. But if a minus x is not divisible by b, then I won't find an answer in between, and then I need to check for a minus qb comma b, and so on and so forth. Now the only question is, how do I find q quickly, right? So let's see how to do that. It turns out that I have assumed that a is greater than b, right? So a will be some quotient times b plus remainder, right? And we know that this r is always less than b. And guess what? This is what we wanted. We wanted the first time where a minus qb becomes less than b. And we know that r is the remainder when a is divided by b. And that remainder is always less than b. So it turns out that q is equals to the quotient when a is divided by b, and a minus qb consequently will be just r, which is the remainder when a will be divided by b. So that means from a state a comma b, what I can do is I can transport to a state b comma a mod b. So you can see here a minus qb is just a mod b and b is just b, right? And I can also check whether from the state in between these two states there is an answer or not, and I can do that by just checking this condition, that whether a minus x is divisible by b or not, right? So if a minus x is divisible by b, then I will just return true. Otherwise, I will recursively go and check for the state b comma a mod b, right? I hope this makes sense. So this was the entire solution for problem D. Let's just have a look at the code for better understanding. Okay, so what I'm doing here is that I'm taking an input a comma b comma x. Obviously, if x is greater than the maximum of a comma b, then the answer will be no. Uh, and also, if x is equal to a or b, or I can get the answer from the state a comma b, that is maximum minus x modulus minimum is equals to 0 or not. Again, the condition here is a minus x modulo b should be equal to 0, where a is the maximum and b is the minimum. So if that is true, I can just simply output yes. Otherwise, I will recursively try to find the answer from a and b. And I will just assume that a is greater than b here. So if a is equals to x or b is equals to x, then I have successfully found out what x is. So I can just return true. Otherwise, the condition to check is that a minus x modulo b has to be 0. If this is true, if this is 0, then I can just return true. Otherwise, what happens is that if a mod b becomes 0, then obviously there is no need because I have reached the end of my recursion. So I will just return there. But if a mod b is not equals to 0, I will just recursively go to b comma a mod b, right? This is another check which is just a silly optimization, that if x is greater than a mod b or if x is greater than b, then also I can return, because both the values will just decrease. I mean, the maximum value will just decrease here every time. So if the maximum value is less than x, then I can never achieve x. So I will just return from there. Otherwise, I will recursively go to the next state, which is b comma a mod b. Right? I hope this made sense. This is the complete solution to problem D. Now let's move on to the last problem that we'll be discussing today. This is problem D, problem E. Now, first of all, talking about this problem had very few solves in the contest, as you can see. But the pretty strange thing about this problem is that it's not very difficult. In fact, it is like, I would say it is easy. It's just that the position of this problem was E and the implementation had some tricks. That is why it is a problem E, and some less people actually were able to solve it. But according to me, this problem was like easy. It's actually a pretty greedy problem. So let's see what we are doing here. So according to the problem, there are n students and we have to pin some messages. There can be a lot of messages starting from 1 to 2 to 10 raised power 5, and we have to choose a subset of these messages and pin them, right? And what happens is that if we pin a message, then every guy reads that message, as long as the total number of pinned messages is less than equals to ki for a particular guy I. And I have already been provided with the ki values for all the guys, for all the children, right? And if the number of pinned messages is less than or equals to ki for the student I, then he will read all the messages. But if the number of pinned messages exceeds ki, then what happens is that out of all those t messages that were pinned, he will just randomly choose a subset of ki messages and read them. Okay, and also for each person I, there is a designated message, right? And that is mi. So what happens is that the professor wants the ith student to read the mith message, right? And what happens is I need to choose a subset of messages such that the expected number, as you can see here. So Monocarp wants to maximize the expected number of students who read their designated messages, right? So for the ith student, the mith message is the designated message. And what I want to do is I need to choose a subset of the messages in such a manner that the expected number of students who read their designated messages is maximized. Okay, that's the problem. It seems pretty hard in the first look, but the magic comes when you start reading the constraints. And the magical part in solving the question is this one, that the value of ki never exceeds 20. So let's see how to solve this problem. So the only crucial observation in this problem is that the value ki never exceeds 20 for any I. And what this implies is that if I pin more than 20 messages, then it doesn't matter how many messages I have pinned. Like if I pin 21 messages or I pin 20 crore messages, it doesn't matter, because once the number of pinned messages exceeds the maximum value of ki for any I, then it doesn't matter, because every student will now just read randomly a subset of ki messages, right? So that is why if I pin more than 20 messages, it doesn't matter how many messages I print, because once I exceed the limit 20, then every student will just pick a random subset of ki messages and read it, right? So the expected value won't change. That's the first observation here. So the thing is that the number of pinned messages should be between 1 to 20, right? Because if I pin 21 messages or I pin 20,000 messages, it doesn't matter, because every guy will just pick a random subset of ki messages and read it if the number of pinned messages is greater than 20. So that means the number of pinned messages has to be for sure between 1 and 20. Okay, great. Then what? Then what I can do is I can actually iterate on the number of messages on that I will be pinning, right? So I can iterate on the number of pinned messages. Okay, so my goal is that I'm going to iterate on the number of pinned messages and somehow calculate that, okay, if I pin I messages, what is the maximum expected value of the number of students who will read their corresponding messages that I can get, right? And the question at hand is that if I am iterating at I pins, I messages that are pinned, is it possible for me to calculate the maximum expected value? And the answer to that is yes, it is. And let's see how we can do that. So what we can do here is we can simply calculate the contribution of every message if we pick a total number of if we pin a total number of I messages. So let's see what I'm trying to say. We can calculate the contribution of each message in the expected value, not message, of each student, or maybe of each message, right? Of each message in the expected value if we pin a total of I messages for all I from 1 to 20. And it turns out that we can pretty easily calculate this contribution, and that is because let's say we are at a student I and we receive these two values, that is mi and ki. Now for every day which is less than or equal to ki, the message mi, if it is included, is going to contribute 1 in the expected value, and if it is not included, it will be contributing a 0, right? And that is the case when the number of pinned messages is less than or equals to ki. Okay, but if the number of pinned messages exceeds ki, then what happens is, let's say I have j days in which let's say I have j number of messages that I am pinning, and that j is greater than ki. Now if that j is greater than ki, then what happens is that the particular student chooses randomly ki messages from the j messages, and if those ki messages contain an mi, then the contribution will be 1, otherwise it will be 0, right? So let's see what I'm trying to say here. So for each message, for each value mi, for day j which is less than equals to ki, what happens is that contribution in expected value if picked, so the contribution of that message in expected value, if I am pinning that message, is going to be 1. Why? Because once I pin it, I'm sure that this particular student will read this message, because the j is less than ki, and if j is less than ki, every student will read every message, and I know for sure that the student will read my message. So the probability of the student to read the message is 1, and its contribution will just be 1 to the expected value. But if j is greater than ki, then what happens is that now I have a total number of j messages, and the student will randomly pick some k1 messages, some ki messages, and will read them. So the probability that my message, which is the mith message, it will be read is nothing but ki upon j, because I have ki messages, and I have j total pinned messages, and out of these j messages I am choosing ki messages, and I want one of these messages to be my message number mi, and the probability of that happening is nothing but ki by j, right? So yeah, this is the contribution if j is greater than ki, and this is the contribution if j is less than ki. So then using this, what I can do is, for all the number of pinned messages, I can calculate the contribution of each message. And then I can simply iterate on the total number of pinned messages, and I can find out the value of the greatest prefix and just add it to my answer and check if it is, and just find out the maximum value, right? So what I'm saying is, if I iterate for the number of pinned messages, then if I am at a value I, then I will pick the highest I elements from contrary I array, where contrary I is an array which stores, so for example, contrary ij stores the contribution to the expected value if we pin I messages, and so what we are doing is we are pinning I messages, and so it is the contribution in the expected value, and it is the contribution of message j in the expected value if we pin I messages, right? So this is what contrary of ij is storing, and once I iterate on the value I, what I can do is, if I am at a value I, then I have to pick I elements for sure, because I am iterating on the number of pinned messages, so I have to pick I messages, and what I will do is I'll choose such I messages whose contribution value is the highest. So what I can do is I can sort these contrary I values and just pick the maximum I values, and out of all these values I can find the maximum, and that is just going to be my maximum expected value. So this way I can greedily solve this problem. So let's just have a look for better clarity and understanding, and let's see what I'm trying to do here. Okay, so first of all, my contrary array is a 2D array of pairs, where contrary of ij dot first is storing the contribution, and contrary of ij dot second is just equal to j. That will come in handy for me to restore the answer later. So this is just that, and now I'm taking in the input of m and k for each value of n. And then what I do is, for all the values of days which are less than or equal to k, contrary of j comma m, that is contribution, if I pick j pinned messages, and the contribution of the message m has to be increased by 1, right? But what is this n here? So this n is this random number, but it turns out that this number is not random. What happens here is that n is equals to LCM of all the numbers from 1 to 20. So I had calculated this previously. So you can be sure that this is the LCM of all the numbers from 1 to 20. And I have done this just to avoid working with doubles. So what I have done here is that I have multiplied all the probabilities by this value n. And I know that in the denominator there is always a j, right? And this j can be from any number from 1 to 20. So if I multiply all the probabilities from the LCM of 1 to 20, then every number will become integral. So that is what I'm doing here. And now for all the values of j which are greater than k, the probability is k by j, and to that I am multiplying capital N, right? That is done. So I initialize my answer with -1, and then for all the values of I, first thing that I'm doing is I'm sorting in decreasing order the array contrary of I, and then I'm taking the maximum I elements from them, and if this cur value is exceeding my answer, then my index is I, right? So finally I will get the index of the total number of days, the total number of pinned messages, and that is my answer, right? So I can simply output answer. And the other thing that I can do is that I can restore my answer, and for that I have my values of dot second in my pair which stored j, and that is why I can use these values now to restore my answer. So I will just go to the first idx elements of country of idx and output their second value in the pair, right? So this will do our job, and this completes the explanation for problem E. I won't be discussing any more problems today. So I hope you enjoyed these solution videos, and thanks for sticking till the end. I will see you in the next one.